This tutorial is about Newton-Raphson method and its implementation. So in your manual, you should see another problem which is related to the deflection in a beam. And we know from our structures and engineering mechanics classes that or mechanics of materials classes that the deflection in a beam is usually described by an elastic curve, and in this case the mathematical model that describes that elastic curve is y, which is the deflection, as a function of distance from one of the edges of the beam, in this case this edge. And the point at which the deflection is maximum is where the slope of the curve becomes 0, which is the derivative of this function. Now the question is to find this location where the maximum deflection occurs. So we are trying to solve where does the slope of this curve become 0. So we're trying to solve this equation by setting dy by dx equal to 0. So if we look at our equation that we're trying to find the root for, then this is that equation. So to implement Newton-Raphson method, we know that we need the derivative of this function, which is given by this, and the implementation can be done by just finding an update from an initial value by updating it with the ratio of the function with its derivative at that initial value. So we're going to implement this. First of all, we need to let's clear our console and let's create the two functions that we are interested in. So first one we will call function fbeam, and we know this function depends upon the location along the beam, and it provides us the value of the function. Let's call it fb. Okay. And then we're going to create a second function which will be the derivative of this. So here are the values for W0, elasticity, the second moment of area, and the length of the beam derived from the problem description. And this is the function which is basically the derivative of the elastic curve, and we call it fb. Actually this should be fb, and this function will return fb when we call it for different values of x, and we save this as fbeam. Now similarly we need to create a second function, and let's call this fbeam prime. And again, this is going to give us the value of the derivative of that function at the various values of x, and let's call this fb prime is equal to. Now some of these things we can just copy paste from here because we have already defined those, and this will be fb prime, and it's the second it's the derivative, so we know that the derivative will be 20 times cube, and then this will becomes 12 times to the power x, and this there won't be any constant term. Okay, so this is our, let's save this as fbeam prime. So with these two functions defined, now we can create the script for the Newton-Raphson method. And we know how this script works. Again, we don't want it to run indefinitely, so it's always a good idea to create a for loop that sets a limit. And we can always say, well, we want to run it for 1,000 iterations, but let's set it for 100 and let's see if it can converge in 100 iterations. And the implementation of this is that my x value, x depends upon some previous x value. So let's call this xr, based, the way we did it in our bisection method, and it depends upon xr old, and then something is subtracted out of that, which is the value of the function, which is f beam at xr old, and divided by value of the derivative at xr old. Okay, that basically gives us our new value, and when we come back and we get here, we want this new value to become the next old value. So we should set our old value equal to the current new value. Okay, of course, the first time we don't have any x old value, so we should initialize here some initialization, which is called xr old, and that can be somewhere in the middle of the beam. Let's say 300 for now, because our beam is 600 centimeters long. So this is basically the implementation of Newton-Raphson method. Now again, we can set up some error threshold or tolerance. Let's say this is 1%, so percent tolerance, and to improve our readability of the code, I'm going to change some of these words to more conventional terms. So often the initial value is called x0, and so we can change all of these x olds to xo, so that we can, okay, and then we can say that x old is equal to x, and then the current value is just x. And you can see how this makes it a little bit more readable. xo is always the initial value, the 0 value, or the x old value. You can look at it from both of those points of view. And at this point, when we calculate the new value, so this will be new estimate, and then after that we will say compare error. So first we need to calculate what is our approximate error, and we know that from our previous codes it's 100 times, and if you remember that we made a mistake last time, it should be the absolute value of the difference between the current value minus the old value and divided by the current value. So this is our error, and then after this we want to check if our error is less than our tolerance, and if that happens, we want to get out of this loop and display the result. And what are we displaying? We're displaying the result. We are also displaying the error, and we are also displaying at what iteration this went out of the loop. So that completes this code. This is ready to run. We will save it as Newton-Raphson, and it's going to run right now and give us that it gave us 268.32 with an error of 0.17 in second iteration, which is very fast. Now I can increase my tolerance to 0.1 to see if I can get a better result, and it gave me even it looks like it has reached that within 2 iterations, because third iteration has also this error is much better than what we already had in the third iteration. So it looks like Newton-Raphson method is the winner, as we saw in the class, and the point where maximum deflection occurs is 268.32. And now we can find out what is the value of deflection at this point by plugging this value into the original equation for the beam, which is the elastic curve. And you can do that on your own and find out what exactly is the deflection at about So this is 300, so this is 268, somewhere here. So we can see this is the maximum deflection point. This concludes the tutorial on Newton-Raphson methods implementation.